There we go. So this is an equation of a circle with center at the origin. So back when we were doing derivatives, we could solve for y in this case, couldn't we? And then, is this a function? Okay, yeah, it's not a function, right? How do we know circles are not functions? Right, it doesn't pass vertical line test, exactly. So we could actually solve for y and then maybe take the positive or the negative root, right, to get the top of the circle or the bottom of the circle. But what we found is it's easier to differentiate this implicitly. And that means we just went term by term and did the derivative rules to each variable instead of solving for one of the variables. So remember when we did that, we said the derivative of x squared is 2x, but our derivative of our y squared is
2y.
Yeah, 2y prime, right? dy dx. We had to do the chain rule there because that variable wasn't an x. And then derivative of 25 is 0. And then we could find an expression for our derivative. And the expression for our derivative is what? Close. Negative x, right? It's negative 2x over 2y. Yeah, and it reduces to negative x over y. Okay? And so we got this expression for the derivative. It was messy. It had an x and a y on it, or in it, but we didn't really worry too much about it because these type of problems were just kind of like, what is the value of the derivative at 3, 4, right? If I put 3 in here and 4 in there, that's on the circle. So at 3, 4, can I find my derivative? How much is my derivative at 3, 4? Yeah, negative 3 over 4. So I could draw that derivative, that tangent line there. Does that make sense? And so when we differentiated implicitly, we didn't worry too much about it because we were always given a point to plug in to find the value of the derivative. And that point always had an x and a y. So we didn't care that the derivative was messy looking. Well, what we were drawing here, this tangent line that has the slope of negative 3/4, that tangent line is actually one piece of a slope field. Like if I asked you to graph the tangent at negative 3, 4, what would the tangent be there? Maybe 3/4. And so if I give you a bunch of points on that circle to graph, what you're graphing is something called a slope field. You're graphing all of the slopes at specific locations by using the expression of the derivative. Does that make sense? So if we have this expression for this derivative, we can generate a slope field across this whole area, as long as we know the x and the y coordinate. The circle ends up being a particular solution. This is the solution that goes through these slope lines, and it's that circle, and it has to have a radius of 5. If I drew a radius of 2, I could get another circle that would go through another set of slope lines. Does that make sense? So what we really were doing is we were generating an expression for the derivative that would let us have a slope, would let us create a slope field. And that's what we're really going to do today, is we're going to take derivatives and plot slope fields, which literally means just plugging in numbers to an expression and plotting the slope field. Okay, but it's a tedious process, which is why you have something on your calculator to help speed that up. Okay. Before we jump into it with both feet, I just want to quick remind you that we're in the last week or so of signing up for the AP exam. Really, my exams that I give you all year long are old AP questions. They're old multiple choices. They're old free responses. If you're getting 3s and 4s on those exams, that means you're really pretty much in the position to get 4s and 5s on an AP exam. Okay, 4s and 5s will get you calculus credit. 3 on an AP exam will get you elective credit. You still get the credit, but you won't count for calculus. It will just count for a general math class. Either way, the more credit you can start out with as a college freshman, the sooner you get to register for your classes, which means you get to register before other freshmen, which is kind of nice. So either way, it's a benefit to have those college credits, whether they count for calculus or count for elective. Okay? Just to kind of give you a general rule of thumb, if you're consistently getting 2/3 of the questions correct on my tests, you're pretty much in line for a 5. Because you only really need to get about 2/3 of the questions correct on the AP exam to get a 5. If you're getting about half the questions correct, you're pretty much in line for a solid 4. Okay? If you're getting 1/3 of them correct, you're pretty much in line for probably a 3. Okay? So just to kind of give you an idea of what the AP exam, how the AP exam is curved. Any questions about that before I move on? Okay. So let's take a look at this expression for a derivative. Now, we're going to throw some fancy terms at you here, but these fancy terms are really just fancy in their name. They stand for things that you already have done. For instance, this expression here is called the differential equation. You might look at that and say, oh, I see a y prime, I'm just going to call it a derivative. It means the same thing. Derivative and differential equation pretty much mean the same thing. We have a derivative here, we have an equal sign here, so we call it differential equation. Okay? And so what we're going to do is we're going to graph this, this differential equation. We're going to graph the slope field for it. So, somehow, just like we were doing implicit differentiation a second ago, we did some implicit differentiation and we came up with this expression for the derivative. And so we're going to go ahead and graph that. And for graphing that, we're going to really start out with just graphing 9 points. So I've got these ordered pairs in a table right here. And all I'm going to do is I'm going to say, Noah, your table is going to graph that slope. You're going to figure out that derivative, the value of that derivative, the value of that slope line. Molly's table, you're going to do the next one. Karen's table, you do the one after that. Aaron's table, do the one after that. Zach's table, where's that? Eric's table, you're going to do the one after that. Alexa's table, you do the one after that. Chris's table, Jasper's table, E, F, G, H. I'll do this one. Careful. We messed up on this first hour. There's a minus sign out there. Okay? So go ahead and calculate your derivative. Put it in the table. Yes, you have. So A, B, C, D, E, F, G, H. Okay, and then go ahead and put the answer to your derivative up on the board. Okay, sweet. Remember, there's a negative sign out front. I get 8 over 5. Okay, I got mine done.
Oh, it was really bad.
Okay. Table G2. Negative 1.6? Okay. Okay, do you notice there are a lot that are 0? Does it make sense that there should be a lot that are 0? You're going to have 0 slope wherever what occurs?
Horizontal.
When what is 0? X or y. Look at the numerator, right? If x is 0, the whole top is 0. Y is 0, the whole top is 0. What does 0 slope look like? What does the tangent line look like? Horizontal, right? Okay, so everywhere we see 0, we're going to put a little short segment that's horizontal. So negative 2, 0. Just a tiny segment that's horizontal. 0, 2. It's a tiny segment that's horizontal. 0, 0. Those are tough to see. 0, negative 2. That's going to be a little easier to see. 2, 2. 2, 2? No, not 2, 2. 2, 0. There we go. Okay. Oh, you know what? I said that, and yeah, I said that, and I wrote it. I put it backwards in the opposite location. 2, 0. 0, negative 2. I think I've got them all. Okay, negative 2, 2. Negative 2, 2. Do we have positive or negative slope? Positive. So we need something that looks like this. Does that make sense? Now, is it not steep, middle steep, or steep steep? It's steep steep. Okay, middle steep would be like a value of 1, right? Over and up the same amount, splitting it right in the middle. So this is going to be steep steep. It's bigger than 1. What about negative 2, negative 2, negative 2, negative 2? What kind of slope do we have there? Positive or negative? Negative, just as steep as this though, right? So we're going to have to the best of our ability, draw something that looks just as steep, but it's negative, it's sloping down. And this is how the AP grades. They look at this and they say, does this look like it has a slope that's bigger than 1? And it does, because it looks like it's steeper than splitting this just directly in half. Okay? And so if it does, then they give you credit for it. Okay, 2, 2, 2, 2. We need a negative slope. So we need something that looks like steep and negative. And 2, negative 2, 2, negative 2. Am I doing that right now? We need this sort of slope. So that's our slope field for that region. Looks something like that. Now it took us probably over 5 minutes to graph 9 points. Okay, yeah, it gets time consuming. They don't want you to spend that much time graphing points, which is why they would rather have you use a slope program, a slope field program. to generate a slope field over a bigger area. They like to see like five out in each direction, so -5 to 5, -5 to 5. If you think about that, that's 11 across by 11 across, right? It's 121 points to plot. Okay, they don't want you to do that by hand. Okay, so we're going to do this slope field on our calculator and throw that picture in. Okay, to get a better picture. And so instead of going out just to 2 in both directions, we're going to go all the way out to about 5 in both directions. So this is how that slope field program works. So the idea here is that this is our goal here is we're going to graph a slope field, and it's going to enable us to sketch a solution curve without actually solving the differential equation for a function. So we're actually going to be able to sketch in a function, and without actually solving this differential equation. Okay, so that's really the key here for the slope fields. So I've got the slope field below. Here's the program instructions. Go into slope field, put in the derivative, the differential equation. Okay, and then I want you to do these standard settings so that we're all looking at the same picture, basically. Now, yeah, okay, good question. People are starting to ask, where do you get the Y from? The slope field program actually uses your alpha key. Your alpha key you activate by using your green key. So the Y is the number 1 button, where you type in when you want to hit a 1. So alpha 1 will get you a Y. Okay? So you're going to put in -2 x variable alpha Y divided by, get some brackets in there. Okay? Program. I bet you typed in the derivative before we hit enter. So, yeah. Oh, yep. So when you do that, you should get something that looks like this. Okay? That's what it should look like. Okay? You notice if you look from -2 to 2, that's this area. If you look from -2 to 2, you're going to see the lines that we got. Right? You can see all those slope fields that we got. Okay? So get a quick picture of that and put it in your notes. Bless you. So, this is your slope field. These are the values of all the derivative. If you would put in -5, 5, -4, 5, -3, 5, Okay, negative 5, 5 would get you that. Negative 4, 5 would get you that. Negative 3, 5 would get you that. Okay? If you plugged in all of those x and y values, those are all the slopes you would get. A little bit of a time saver. We're gonna now show you how to graph these particular solutions. Okay? So we're going to graph the function that goes through those points. So here is 0, 2. If we want to graph the solution that goes through that point, what we do is we sketch something in that follows the tangent lines. So we know that at 0, 2, we need to have what sort of characteristic at 0, 2 that has 0 slope?
Needs 0.
What has to be true about my function if it's got 0 slope there? Where on my function, if I have a function, where on my function do I have 0 slope? 0 tangent line.
Sides,
Max and mins is, yeah, tops and bottoms, max and mins. So if you notice, everything slopes away, down and away, and down and away. So is this a min or a max? This is a max. So we're going to make sure that we have a max here and then that we slope down and get flatter because that's what these tangent lines are doing. So you notice how I've kind of matched that slope line there. Unfortunately, you can't see the slope line here because of the text, but there's one right here as well. Okay, so if we're going through 0, 2, that's a possible solution to that differential equation. I don't know what the function is. I couldn't tell you what the equation is, but we don't need to know what the equation is. We just need to be able to sketch the solution. Okay, so we know that since our tangent lines slope down and away, our function better go down and away in that direction. Since our tangent lines slope down and away in this direction, our function better travel down and away in that direction as well. Okay? What about 0, 5? 1, 2, 3, or whoops, 1, 2, 3, 4, 5. 0, 5 is right here. What is that going to look like? Pretty similar, right? We're still going to have to slope, but we have a much higher slope here. We're still going to have to slope down and away. We're still going to have to slope down and away. I'm going to try to go through this one approximately down and away, and approximately down and away.
How do you know which one it goes through?
You just estimate. So I usually pick one on either side that I try to match, and then I try to match one kind of close a little farther out.
Because if you did, like...
We know it can't go way out here, because these aren't that flat. Does that make sense?
Yeah, I guess.
You know, we've got to go down pretty fast, because these are pretty vertical. Does that make sense?
Like if the first one went to that one, wouldn't the one that you just drew technically go to the one above the one you drew to?
Like through this one?
Well, like so that one, like 2 goes through that one, and 3 goes through the next
like
one.
Like this one?
And 4 goes, yeah.
Not necessarily.
Okay.
I mean, because this is much more vertical than this, so this has got to drop faster than this.
Okay.
Okay? So that's how we're kind of reading our slope fields. And so this being much more vertical, we got to drop faster. Okay? And then if I go to the other side of the axis, and I want to graph a possible solution through -3, is that point through -0, -3, is that going to be a min or a max? Min. And then I'm going to try to, follow these tangent lines here. I'm going to slope down fast and then get flatter. Slope down fast and then get flatter. So depending upon, kind of like the circle, depending upon where you started, you're either going to graph the top of the circle or the bottom of the circle for a function, right? Because you can't graph both and still have a function. This function happens to be the same thing. Depending if we're starting above the axis or below the axis, we're going to graph a part of it. Not all of it, but a part of it. Does that make sense?
Just curious, what kind of application is that?
Good question. Has anyone seen something that looks kind of like slope fields on TV? Weather. What sort of thing?
Pressure.
Okay, wind speed, wind direction, high and low pressure. They call them pressure gradients. And what they actually do, they're actually drawing these families of solutions. Like when you look at high and low weather, high and low pressure weather maps, they have all of these lines that look like they converge and then spread out and converge again. It's exactly these families of functions that they're drawing. So where the curves get really close together is where we see the really dense or really high wind speeds. And where the curves get really far apart are where we see the really low density or really low wind speeds. Okay, they're actually graphing those families of curves.
How do they come up with
The data?
Yeah.
Doppler radar sends back information on wind speeds. So I don't know if they actually really ever deal with the slope field, but they deal with the family of curves. Any other awesome question? Any other questions? Okay, so there's how we can sketch a family of curves once we have the slope field in front of us. We just have to make sure that they follow the slope field. You know, things like we would never graph something that looks like this that cuts across tangent lines because we know we have to flow with the tangent lines. So that's always a dead giveaway that that can't possibly be a solution if it starts crossing the tangent lines like that. Okay, so I want to kind of switch gears because there are some differential equations that we can solve. Okay, and certainly not the one that we were just dealing with, but this one we can solve. This one we can do something that's called separating the differential expression. Okay, so we call that separable, and we actually can then integrate it. Now, when I talk about a separable differential equation, it's a fancy term. It's not as difficult as it sounds. What it basically means is getting all the y's and the dy's on one side and getting all the x's and the dx's on another side. That's what it means. So, do we have any y's in this expression? No, but we do have x's and dx's. How can I get this dx on the other side?
Multiply it by dx.
Does that make sense? It's a fraction. If we multiply both sides by dx, maybe I need some brackets here because that side has multiple terms. Then I've gotten the dx and the x's all on one side. Okay, how many are okay with that? Feel kind of comfortable with being able to shift it like that? We're really not multiplying. We're doing something really fancy that's called separating the differentials. Anytime you see a little d, that's a differential expression, right? We took the deltas and replaced them with d's way at the beginning of the year. Okay? It's really mathematically the same as multiplying through, just what Noah said. All right? But we really technically call this separating the differential equation. So when we separate it then, we end up with dy on one side and 1 over x squared plus x dx on the other. Okay? And so since we have that separated, what we're going to do then is we're going to integrate or take the antiderivative of both sides. Okay? And so just like working with any equation, what we do to one side, we have to do to the other. If we're going to take the antiderivative of the left side, we have to take the antiderivative of the right side. So the question is, which one is easier for you to take the antiderivative of, the left or the right? The right side? The left side? Okay.
Right.
The right side? I got one right, one left. Depends. What is the antiderivative of the left side? It would. Does that make sense? The antiderivative of dy is just y. How come? Okay, yeah. What is really here? What number is really here? 1. And anytime you take the antiderivative of a constant, you get a variable, right? Like if we integrated that with respect to x, 1 dx is just x. Okay, so 1 dy has to be y. Some people saw in first hour the right-hand side being easier because it had x's in it and they were familiar with it. They didn't quite know what to do with the dy. But the idea is once we get the dy by itself, integrating a dy just gives us a y. We might have something here to integrate, but in this one we don't. What about integrating then, or taking the antiderivative of this? I'm going to rewrite it to that so it has that negative power, so it's easier to do to reverse the power rule on. What is the antiderivative of x to the minus 2? Bump up the power by 1, it becomes what? X to the minus 1, divide by that new power. So there's the antiderivative of x to the negative 2. What's the antiderivative of x? Yep, bump up the power to 2, divide by 2. And then when we do antiderivatives, we always put what out here? Plus c, exactly. We've got that constant of integration. That constant of integration, if you think back to the last page, that's why we were able to draw 3 curves. We changed the constant to get the first curve, and then we changed it again to get the second curve. We changed it again to get the third curve. That's that constant of integration. It's that shift. You notice how those curves are just shifted up or down? And that's what plus c does, right? Doesn't plus c just shift this up or down? Okay, so that's what allowed us to graph a family of curves on that slope field. But we want one particular curve, so we're going to have to deal with this c. Yeah. Well, think about it. Anytime we take an antiderivative, once we do the rule, it takes away the integral sign and the differential, right? We did the rule, those both disappeared. So we did our rules. Oops, excuse me, we did our rules, so these both disappear. Okay?
So you don't keep the x like you do with the y.
No. The reason why we have the y is because we had the 1 there. Not because of the integral sign or the dy, but because we were integrating a constant. Does that make sense?
Well, wouldn't there just be a 1 on the front of the dx also?
Like over here, times 1,
No, but in front of the dx.
right here.
Yeah, like.
Well, there isn't a 1. There's all this in front of the dx. Okay, does that make sense? We don't have a 1 out front here. We have all of this stuff. Okay, so we have to simplify this a little bit. What's x to the minus 1? 1 over x, right? So we have minus 1 over x. So I'm just going to call it minus 1 over x plus x squared over 2 plus c. But I want to graph the solution. Now this goes back to the last page. I want to graph the solution that goes through that point. What are the coordinates for that point? What's my x coordinate?
2.
My x coordinate's 2. What's my y value? 1. right? When x is equal to 2, we plug it in and we get a value of 1. So if I plug in 2 and 1, what do I get for C? That's 4 divided by 2, so we have 2 here. What's my value for C? Negative 0.5? So my particular solution then, that goes through 2, 1, point over there in the first quadrant, looks like minus 1 over x plus x squared over 2 minus a half, 0.5. Okay? So the last activity is down below. And you're going to graph the slope field and you're going to put in that particular solution because you can put in a solution. So don't forget that the slope field y prime was, I can't remember now. What is it? Oh yeah, 1 over x squared plus x. 1 over x squared plus x. So you can put in that slope field. And you can put in a known solution that's option 2. So you can put in that equation from your known solution. Put in that slope field. And you can graph the slope field and the solution all on one page. Okay? And when you do that, it looks like this. And if you notice, we get 2 curves. We have those 2 curves. Which one should we really be paying attention to? The curve on the left or the curve on the right? Yeah.
Why did I get a positive 0.5 for C1? Because
Well, this is 1.5. 2 minus half.
Oh, I forgot those 2.
Oh, sorry. So left curve or right curve? Which one do we have to pay attention to? Knowing that our solution has to go through 2, 1.
Probably the right curve.
The right curve. Exactly. 2, 1. 2, 1 is right here. So we would just sketch that right curve. We wouldn't need to worry about the left curve. Okay? Tomorrow we'll get our test back and we'll have some time to work on this stuff.
As far as you
Yeah.
sign this